And I hope you see the presentation. Now,
Yes.
Let me quickly put the full screen. So you
Very
see
good.
the full slide,
Yep.
right?
Yep.
Yeah. Okay, so welcome to the ABB presentation. It is on showing the ABB landscape in battery storage, and to explain to you how this battery landscape is built inside of the company a little bit. So I don't need this slide anymore. Thank you, Christian. We are two of us, and I will have the first half, a little bit more than maybe the first half, and then Lorenzo will take over. First, I would like to explain a little bit on the ABB setup and situation. And this slide you see here is an official slide from the ABB group that is usually shown externally. So yes, you know probably that ABB is a big company, in total more than 100,000 employees in more than 100,000 countries and so on. This is what probably you see from outside when you hear about ABB and so. But if you look inside, ABB is structured in a special way. So there are first 4 different business areas, so-called, which deal with specifics in industry. For example, the power grid electrification is one, and then motion is one, which deals with motors and the drives that are needed for those motors and so on. And then process automation, which is more for the chemical industry and other industries that use systems that need to be automated. And then robotics for different industries also. And now if we look into these divisions, the title of the slide says fully decentralized business model. This means that inside ABB there are 20 divisions that act like single companies. So each of these divisions has a certain market, a certain technology portfolio, and so with 20 divisions, it's about 5,000 people per division in average, which is kind of almost like an own company. And if we look at the battery solutions, there are different divisions having battery solutions in ABB. And this is what you will see now in this presentation, examples of some of them. But you have to know there is no single battery center of ABB somewhere sitting. It's really distributed, and each of these divisions have their own R&D and product development and so on. So this is the situation that we have today, and you will see a few examples on it. So the agenda is as follows. We will first have one slide on the positioning of ABB in energy storage. And then we go into examples like solutions for stationary and in the transportation sector. And then Lorenzo will take over into more deep dive, especially for the rolling stock application, so heavy duty applications in transportation, how we select the battery there, and the digital solutions that we have in that specific example. The picture is a bus in actually Baden, where we both are located, which is equipped with ABB battery. There is one line in Baden that has been fully transformed from diesel to electric, and you will see later the battery here is on top of the bus, and this is a special development that has been done locally here in Switzerland. But first, the introduction on ABB's positioning on storage. So one thing is very important. ABB does not manufacture battery cells. There is no chemistry factory that would produce any lithium-ion cells or something like this. ABB buys them from manufacturers in Asia and also from Europe and so on. Then ABB selects the optimal battery technology, depends on the application, can be lead acid. I will just show a few examples below afterwards. To serve that specific segment, and thus then product development and system integration. So the batteries that ABB uses at the moment for this kind of solutions, or not only batteries, also electrolytic double layer capacitors, supercaps, sodium-ion batteries that are used. We will see an example afterwards. Lead-acid batteries is also used a lot in uninterruptible power supplies. Nickel metal hydride batteries also in data centers. Then some lithium-ion chemistries, NMC, LMO, LFP. Then lithium titanate batteries in rolling stock applications. And then NMC, LFP also for stationary containerized solutions. So these are all batteries that ABB buys from external, does some integration, for example, producing modules out of single cells or full containers, and then has those solutions on the market. If we look at the different applications, we have stationary on the left side, and examples on transportation on the right side. And for most of these examples that you can see here, I don't need to go into the details, but for most of them, there is solutions that ABB has to sell to the market. What we do not do anymore is small residential batteries for homes, and what we never did is batteries for personal cars. This is, of course, the car industry that serves this, but we do for ships and for trains, and you will see the examples. So let's go first into the stationary segments. Typical example is so-called e-storage flex. This is the name of the product that is in one of those divisions that I have shown at the beginning, which is, as an example, a containerized solution where for smaller systems, everything is inside of one container, from including the batteries, the power conversion, the transformer, the cooling, and the DC and the AC switch gear, so the breakers and everything. So here you see an example of these specifications. It can be small. It goes up to a little bit more than a megawatt, and a little bit more than 1.5 megawatt hours. And then it can be connected to the loads that are needed. Here will be some links to look at if you are interested to know more details about it. A concrete example is to use those containerized solutions for EV charging support. So here you see on the picture, there is an EV charging station that has a limited connection to the power grid. So when all these Teslas and other cars want to charge with a high power chargers, then the battery can act as a buffer and help to keep this power available. So here you see the power grid. The battery is located here. It injects power into the high power charger if needed, and if not, it can be recharged. So this is a typical example, and several of them are being sold in the market in Europe at the moment. Another segment is uninterruptible power supply. So this is a backup in case of a power outage in the grid. This is a huge market for ABB also. So typically you have the power grid that should deliver the power to the end customer, which can be a hospital or a bank or whatever is a critical load. And in this picture, you see a so-called double conversion concept where always the power goes first through the UPS system. It flows through it all times to serve this end customer. And in case of a trip of the power, the battery is connected here directly. So the load does not even realize that the power grid has tripped. And then there is a bypass for doing maintenance and so on. But basically, this is a concept that is used a lot. And in some of the projects and products, more and more, there is internally in this UPS several modules that work independently of each other. So then if a module is tripping, the others work continuously. So there is no outage for this, and maintenance can come and replace a single module. So these are important concepts that are, but this is a world on its own with many different versions and many different markets, from industrial to commercial to private and so on. One large example is a medium voltage UPS, for example. This is a big cabinet which includes the batteries also. It can be lithium ion, can be valve regulated lead acid, it can be supercaps. In most cases, it's actually still lead acid. This kind of solutions are used a lot. For example, I think the hospital in Basel uses one of these, and then banks and industrial customers and so on. So this is an important example. Then if we go to the small size, there is also UPS is on very low power and small size directly put into some cabinets in data centers where you have the data center modules that store data and so on. But then on the side here, batteries are inserted. There is rectifiers with DC modules that. So you have the UPS inside of this edge. It's called edge cabinet as a product line. And the batteries are typically nickel metal hydride in these data centers, especially in US, or sodium ion batteries, also especially in US, can also be lead acid. So the advantage here is that the UPS is not a traditional large UPS that is outside, but each of these cabinets gets his own UPS, so it's quite a good redundancy on this. Then one last example for the stationary, which is called wayside energy storage. It is for trains and trams, but it's stationary. So it's located at some train station or close to the line. You see here, power comes from the power grid. The AC power grid is, for example, rectified, and then the tram or train gets the DC electricity. But then there is here this buffer battery connected also. So when the train enters the station, the braking energy is used to charge the battery. And afterwards, when the train is moving again, the energy from the battery is used, coupled into the overhead line of the train system, as an example. There are different configurations, but one example is what you see here on the picture. This is an example from Australia. It's a 1500 volt DC system. What you see on the map is 3 train stations, but only here on the top and here on the bottom, there is the connection to the main power grid. So, and the distance is quite long. So when the train in this train station is starting, in the past, there was always some power trips because the line is simply too long to serve, to feed the need of that train. So instead of adding another substation to the main grid, supercaps have been installed here that can use the braking energy of the train when it comes and also be charged separately, and then be used for acceleration of the train. So this is a typical example, and there are quite a lot of them. This is a very specific market with very specifics in the technical need of such a solution. So it's not a normal BESS that you would find otherwise. There are specifics there. So then let's move to the onboard examples. And this again is a different division, and in this case it's actually one in Switzerland. Serving onboard batteries for buses, for example, or trains and other vehicles. So one example is what you have seen before at the slide with the agenda. So here is the bus with the battery on top that is produced in Switzerland, the modules and strings and the pack, and then the converter to drive then the motors. The motors is also an ABB product, and there are more products in this kind of vehicles that are from ABB, but most important here in this is the converter and the battery. Another example is batteries for trains. There are different constellations. Sometimes the train has no electric overhead at all, like the picture here. So then the train is switched from diesel to full electric, for example, using LTO batteries in this case. There is a link if you want to read into this then. In this case, it's in the north of Germany. 55 of these trains are now equipped with the ABB batteries. There are also examples where there is locomotives running on diesel hybrid electric, where the diesel engine is always used as the main energy delivery, but a battery is added to again recuperate the braking energy and being able to accelerate at the train station with not so much exhaust from the diesel engine. And this can save a lot of diesel also, 15% or 20%, and this is quite a lot. So lots of trains with the diesel engines are also equipped with batteries. Other heavy-duty applications is off-road mining vehicles. Here an example where you can also read more details here. This vehicle is bigger than it looks on this picture. You see the driver here. These wheels are 2 meters in diameter, and it can carry 160 tons. So imagine a truck on the road is maybe 20 tons or maybe 40 tons, but this is 160. And more and more mining vehicles are equipped with batteries. Also those going underground, because if you have a battery vehicle underground, you need much less ventilation in these tunnel systems compared to diesel mining vehicles. And this is quite a trend now to have it. And here you see different solutions that come from ABB then, but always again this string that we have on the picture. And this I would like to explain a little bit more. So the string internally has modules, typically 12 to 13 or something in that range. One module has typically 48 single cells, LTO, lithium titanate cells. And then these strings are then combined in parallel, typically 6 or so of these strings. This picture is an example on the situation when the pack goes onto the top of the train. And there is also other constellations where the battery goes underneath of the train and so on. And often there is several of these on a train. Of course, trains outside, they have a large temperature spread in usage. So we have inside ABB, the division has developed this quite rugged solution, I would say. In Switzerland, there is the manufacturing of these packs. So you see here, first the cells are delivered from the supplier. Then they go into a robot station where cells are picked and put into a module and then laser welded for having the cell-to-cell connection. Then it's tested on a module tester quite in detail. Then it's packed into several modules, into a string and into a pack, and then tested again. And if you want to see a little bit more, there is a movie that you can have a look at, which shows the details on how the robot is picking the cells and put them into the module, and then the laser welding and so on. That is available here on YouTube. What I did not show now is examples on marine, where we have also examples from another division equipping large ships with actually quite big batteries of several megawatt hours, several megawatt. It looks like stationary storage containers then in big ships, but this we have not included, but it will be. You can have a look then on the slides. There will be in the slide set. You can have a look at that also. Okay, so this is the first part of the introduction of the presentation on these examples. And now I would hand over to Lorenzo, who would explain how we did selection of batteries for rolling stock applications, and then also go into digital capabilities that we have.
Okay, so hello everybody. Let's start the second part of the presentation then, battery selection for rolling stock application. So first, if we take up this picture where we see a little bit the battery landscape, we see in these two axes the gravimetric energy density at cell level and the volumetric energy density at cell level. And we see the lithium ion state of the art here. We also have a big spread, so depending on the actual chemistry which we have. And we see that the LTO that Daniel was mentioning before, here we are on around 100 watt hours per kilogram, quite on the bottom left part of the graph compared to, for example, other chemistry like NMC. Basically, this would tell that the LTO is not the best chemistry when it comes to energy density, but this picture doesn't really show the full, or just show part of the picture. Because if we see then in the next slide, LTO has also unparalleled advantages, especially when it comes to cycle life. So in LTO anode, we can have up to 20,000 full equivalent cycles of 100% DOD and 25 degrees. And this number is much higher if you look, for example, compared to NMC, LFP, or other kinds of chemistries where you have a few thousand. Also in LTO, we have generally a higher C rate, which means the battery is particularly suited for power application, that you can have up to 3 or 4 C of continuous charge-discharge, also symmetric. And therefore, it's, as I said, it's a good power capability, especially in application where, for example, as Daniel was mentioning, you have recuperation of braking energy from the train, from vehicles. And third, but for sure not less important, is safety. So compared to graphite-based cells, LTO anode has a higher potential with respect to the lithium metal of around 1.5 volt. And this safety margin, of course, on one side, we have an overall less cell voltage potential, but we have a safety margin that protects us against lithium metal plating. Lithium metal plating, which of course could then produce with aging the deformation of dendrites that could lead to, for example, internal short circuit. So LTO somehow LTO has this advantage, and also has the advantage of having negligible volume expansion and reduction when you cycle the cell. In this sense, it's then a safe cell that has inherent electrochemical properties that make the cell safe. We have a higher power capability and a long lifetime. If we take an illustrative example, we see two different fields. One is the railway, one is the car industry, and we have a big variation between the two. So in operating hours, for example, a railway vehicle operates for maybe 6,500 hours, so maybe 18 hours per day, whereas the car has only 250 hours per year. We have 200,000 kilometers per year, whereas the car has only 13,500. So we are factor higher in rail compared to cars. Also, when it comes to, for example, to energy throughput per year, in rail we speak of around 1,000 megawatt hours per year, whereas the car is only 3.4, so it's a factor 300 higher. And this motivates, even if of course qualitatively, the need of a cell that allows us long lifetime, and also shows a little bit that our requirements are not the same as the one in the automotive market. So putting it up together, LTO is somehow it's a good choice for railway industry because of the long lifetime and the continuous operation which we have each day. The safety, since of course the trains can operate vehicles in critical environments, so underground or badly accessible, and the performance that allows us to have a high power, which means recuperation, for example, of braking energy and fast charge capabilities in terminal station. So this is for what concerns the selection of the cell chemistry used in ABB borderline ESS products on rolling stock. What it comes on top is the digitalization strategy of ABB motion traction. So we develop our own batteries, our own ESS, and then on top we have also a digital strategy that allows ABB and the customer to profit also from the data which is produced within the battery. We have mainly three pinpoints here in this slide, or three focus topics. The first is that we want to have intelligent products that are connected, that can store data into the cloud, and that afterwards we can use to visualize data as well as to do some analytics with that. The second focus topic is the customer support. We want to have automated data upload, and exactly using this information or the data that is coming from the battery, for example, we can provide a higher level of support remotely, for example. And third, we have an added value because of the continuous monitoring of the system, of the ESS, for example, allows us to deploy strategy that go in the direction of predictive maintenance, for example, or estimation of parameters within the cell. And there is also space for co-creation, such that the customer and ABB, they can also discuss together and of course implement a solution within the cloud that in which the customer can also profit. This was in general. When we couple it, so when we do it specifically to ESS, what do we have is that we have an energy storage system running in the field on a bus, on a train, and then we have a second digital product. The first step which you have to do is to connect the battery to the cloud. Our batteries, they have, of course, a controller that can be connected to a remote conditioning unit that is the gateway to the cloud. And afterwards, then we have data visualization. So the data that is collected into the cloud is then available to the operator, can be visualized. We can do fleet analytics and fleet monitoring. This is a little bit of a sort of slide with many items, but more or less we have already seen part of that. So starting from the In the field devices here, we have a connectivity layer, and then data is sent into the traction cloud, needs to be decrypted first. And there we have a sort of ABB portal where data can be visualized and further used to feed algorithms. Now this red part here also further decomposes in other steps, which are doing a little bit more in detail here. So decryption, storage of data into a cloud. What is maybe important is exactly this data analytics part, because we don't just visualize, for example, cell voltages or currents, or how the battery is operated, but we can use this raw data to perform some additional computation within the cloud and to allow us to extract some hidden variables. So estimate, for example, some states which are generally hidden. And now we can do a small tour of the portal. I took some screenshots of how the RCM, so the remote conditioning monitoring portal, looks like. This is, of course, shown on a demo fleet, so that it's purely used for purpose of showing up. And you see we have a demo fleet. Inside this fleet, we have, in this case, is a diesel hybrid train. And then one layer below, you also have the single ESSs, the single batteries, where you can see information like counters, so capacity counter, energy counters, the overall battery voltage, the overall state of charge of the battery. Getting back onto the vehicle level, it's possible to see on several days, for example, how much the battery was reliable. In this case, reliable means error-free. The battery could be operated without any issue or trip. Of course, this bar should be green as much as possible. And in this gray portion is where we don't have data to sort of visualize or to do. Basically, we have missing data here. And we can also have histogram, where we see basically how much is the battery operated per day. So in terms of hours per day, operating hours per day. And on the right, we have, for example, temperature histograms, where you can see basically how many hours your battery was operating on a given temperature. And then you have also a budget. This is not cumulative, so it's not meant to sum up to the number of hours which you have in this time frame. But for example, can be used to notice if the battery was used for too long or was used long enough in too hot condition or too cold condition. This information can be used then to visualize the data and to modify, for example, the strategy. Not just that, we have also a utilization pattern profile or tab still on battery level, where, for example, you can set up, or it's possible to set up some thresholds. So not just temperature, but for example, also state of charge boundaries or cycles or C rate. And then if the battery is operated, let's say outside of these thresholds, so at temperatures below 0 degree or at state of charge below 5% or greater than 95%, or the same for cycles and C rate, then you would see, let's say, the building up of a red bar here. And again, this can be easily seen in several days. That's for what comes about simple KPI visualization. We also can do, of course, time trend, such that it's possible to show some relevant variables on a given battery, basically on the whole fleet, when it comes to state of charge, temperature, usage, voltage, and current at several sampling times. And as a final slide, I mentioned at the beginning, we had also a little bit of, or we have also data analytics, not just visualization of data. And this data analytics was not fully shown in the portal, but we also have in parallel digital twins or battery models that are running exactly in parallel, and they are fed with the input measurement coming from the field to the cloud. So in this case, in blue, in this plot, you see the measurement coming from the cloud, for example, battery or cell current. And so blue is measured and red is instead our model. And you can see that feeding the current to our model pretty much produces the same voltage response. We can use the digital twin to do parameter estimation, which means that in the cloud, we can monitor our batteries. We can estimate quantities like state of health, for example, defined as capacity fade, or as in the right portion of the slide, we can also estimate other model parameters like internal resistance. In this case, it's again a general plot, but you see that in several months in the year, we have a lot of estimation points. We can do a box plot, and with that, we see that the median of the estimated points of the set of estimated points collides or agrees well with the theoretical value which we expect. So concluding, doing a summary, we have seen offering of ABB energy storage products and systems, stationary application up to large scale. Then we have seen a range of UPS products and stationary application also for railway, like wayside and airborne solution. And then we haven't seen the storage solution for marine application, but Daniel will have the slide inside the presentation. We have seen an overview on cell selection strategy, and then explore together in a really short tour the ABB motion traction remote conditioning monitoring portal, where KPIs, variables, and analytics can be done on data coming from the batteries in the field. Yes.
Yeah.
Okay.
Thank you very much, Lorenzo and Daniel, for this very interesting insights. For me, totally new is that we already saw in the chat, meanwhile, the discussion that there is business going on between different companies. So there is actually big interest in your product. So that's great. But I would also now ask the audience for questions towards the people. Please take the possibility to get in touch directly with the expert from ABB. We have Marcel Held. Just a question.
Yes, can you hear me?
Yes, yes.
Yes.
I have a question maybe to Daniel. In your data center solutions, you use sodium-ion batteries and nickel metal hydride batteries, but not lithium-ion. Is there a specific reason that you don't use lithium-ion?
Yes, in data centers. So this was an example of a division based in US mainly. And in US, lithium-ion batteries are not allowed in data centers.
Oh, okay.
This has historical reasons. There was once a fire on lithium-ion batteries in a data center, destroying the data center basically. And then there was a regulation made, and this is not is still in place. So once some regulations are written down, it's not so easy to kill them again. So the division has, of course, tried to use, for example, they were interested in LTO because this would be an ideal solution. It's not straightforward. So that is the reason. So lead acid, nickel metal hydride, and sodium ion is all fine. Lithium ion still not. Maybe with some tricks and it's maybe possible to enter into this, but that division has decided not to pick that battle.
Okay, thank you very much. Very interesting. Yeah.
Thank you very much. Maybe Daniel, you can stop sharing the screen, otherwise it looks a bit odd when. exactly. Then we have another question from Vincenzo.
Yeah, thanks a lot for the presentation. Here from Hilti. Actually, I have two questions for you both. First is if you are addressing as a research team the topic of Second Life. I mean, you're planning to do activity there and the activity which goes towards product. What are the legal, let's say, constraints for the Second Life? And there for you, Lorenzo, more the question is, do you do only active control of your battery system or only monitoring activity?
You start, or
I can start, yeah. I mean, Second Life is a topic that we discuss regularly. And of course, we are interested. The point is always who is responsible for the battery if something happens. So if ABB uses Second Life of another company and then things go wrong, there is the ABB logo on that solution. And then the question is who is liable and so on. So that is one thing. The second is how can we make sure the quality is okay of those batteries, because we did not have them in the first life. So usually,
I was thinking more if battery that you install or if you, for battery that you have full control, let me say.
Okay. Yes, that is a topic that we are looking at. For lithium-ion, we do not have yet Second Life batteries because they live for many years, and the business is ramping up now. So we do not have any Second Life options at the moment, but we are looking into this. Especially interesting for us is that we actually know exactly what the battery has seen in his first life, which is, in our opinion, a very important piece of the puzzle, so that we can really distinguish and sort out those who have been kind of abused during the first life, then we would not use them in Second Life, and others that have seen always a good behavior or have been treated in a nice behavior, that those we could then use. But we do not have any official business at this at the moment.
Yeah. Okay. Thanks.
So Vincenzo, concerning the control, you mean in which direction? If we also provide converters to actively control the battery, or if we also have a backward link from the cloud portal to the battery?
Exactly. If you detect, for example, your battery is aging faster than predicted, you change a little bit like the operative state of charge range, for example.
Yeah, I mean,
things like that.
The control of the battery, we provide the battery as a system and the converter, but then of course the actual power that is cycled depends on the application, that depends on the vehicle integrator.
Yeah.
What we do is that of course we provide limits to that, but these are mainly limits which, if respected, should not produce like an overvoltage or under voltage or that. So the responsibility of usage of the battery depends on the cycle, which then depends on the vehicle integrator system. Yeah.
But you don't have you don't sell I don't know, a software controller where you say, okay, we have a special controller which is able to monitor the state of life, for example, of the battery pack and update the limits in order to enhance a certain objective function, or like lifetime rather than cost or stuff like that.
Well, I mean, this is then disconnected from the cloud, clearly. But of course, we do have algorithms which are specific to an application. Yes, they don't go into the cloud in this sense, but then locally into the system, they can monitor state of charge or state of health. Exactly.
Okay, so it's monitoring. It's not like, for example, Tesla today is already updating from the cloud the battery operative limits of the pack, according to what they detect, and so that's passed via the clouds, and then they send back to the car.
Right. At the moment, we have only the upstream link, which means the information that is coming from the battery, the operative information is going into the cloud, where then you can run your analytics. But we don't have the downstream link, that means from the cloud to the vehicle. There are a lot of cybersecurity requirements and so on, which at the moment
because the system is not yours. Yeah, that's true. That's also the difference. Yeah. I was missing these small details. That's like somehow the easier control of the cars. Yeah. Thanks, guys. Yeah.
Well, thanks a lot. Are there further questions towards Daniel and Lorenzo? If not, I would say thank you very much to both of you, to ABB, to give us this insight, especially everything what was about software. That was very interesting and novel to see what ABB is already capable of. I would, for the end, again, advertise, of course, our next Battery Tuesday, which will be then from a world global company to a small startup, 8inch, which is in the field of solid-state batteries and then the production of solid-state batteries. And also, again, for make advertisement for next week, for the March 15, for this webinar together with Swissmem about IPCEI. So I hope to see some of you also there. Thanks a lot, and hope to see you next time at the Battery Tuesday.
Thank you.
Thanks a lot.
Have a nice evening.
Thank you.
Thanks.
Bye-bye.
Bye.
Thank you.